In 16.4, we're going to deal with something that you will not be tested on, as you'll see in the notes packet, but this is something you'll talk about more in Chem 2, and it is included in this chapter, so we'll go through this section briefly. So in section 16.4, it delves a little bit more in depth about what happens with specific salts, which remember are just ionic compounds, when placed in aqueous solution. So in general, a salt is just something that's an ionic compound. But specifically now, we're looking at typically when you have a hydrogen ion with an anion, and then you replace that with some sort of metal. So in other words, big fancy name for an ionic compound. Now, when you have a hydrolysis reaction occurring, what we know is that those ions will interact with water, some of which will produce acidic solutions, some of which will produce basic, and some will actually produce neutral. So a lot of what we've been writing were actually hydrolysis reactions, but some were a little bit different. So in general, we can make a couple statements. One, anytime you have an anion that is the conjugate base of one of our 6 strong acids, so that would be Cl- for HCl, that would be nitrate from nitric acid, that would be the bromide ion from hydrobromic acid, the iodide ion from hydroiodic acid, and the chlorate ion there, perchlorate. Those would all be considered situations where they would have actually no effect on the pH because they are such weak bases, because they were from such strong acids, they will actually all produce a neutral solution. Now notice I did not include sulfate in there. That's because sulfuric acid, because it is diprotic, will be a little bit different. Another basic pattern we'll note is that your alkali or your alkaline earth metals, so basically group 1 and group 2, will have no effect. In other words, they will also be neutral solutions when in water. So that's basically all summarized in this table. We'll come back to that example in a moment. So this table is in your book on page 599. And this summarizes those things we just mentioned. So here are our conjugate bases of our 6 strong acids. Notice that they have no effect. They will result in a neutral pH. And then our alkali and alkaline earth metal cations also have a neutral net effect. Now these other ones that produce basic and or acidic solutions, essentially the best way to do these is just to memorize these, but this is why we are not going to be testing you on this, because there are other things that we'd rather have you worry about right now. So if you kind of keep track of these basic ones with the neutral ones, that's good enough. But we can write some reactions just to show how these other ions would produce basic or acidic solutions. So if you look back at that example at the bottom of page 8 that we just skipped over, it was asking you to write this interacting with water. So I'll do that down here just so we can see that. So if I write this ion here, and we interact this with water, you may not necessarily at first know what to do with that. But if we find that up here in our list, you'll see that it says right here, hydrated metal cations, so in other words, a metal mixed with water to create an ion, will actually result in an acidic solution. So we know that that means that acids donate a hydrogen. So somehow this needs to donate a hydrogen to the water molecule. So whenever you see something like this where you have water molecules in there, it's a set pattern. What happens is one of these water molecules, there are 6 of them, one of these is going to break up, transfer a hydrogen to this, and then this would now become 5 full water molecules and basically a hydroxide at the end. So what we'll see there is that would result in this. Iron, one of the waters is going to be broken up, so instead of 6 we'll have 5, and then what will be left after one of those hydrogen transfers would be an OH minus. Now this was +3 overall, but if we now are putting a -1 with that, that's going to be +2 left over, and then we would have a hydronium ion resulting as well. So this is why we actually get an acidic solution, because it's producing that hydronium ion there. Once again, we will not ask you to memorize this section, but we are putting this here just so you can check that out. If we look at one more example with these, it's asking for each of these salts, would the solution be acidic, basic, or neutral? And then it's asking you to write a net ionic equation for those active ions, in other words, the ones that were acidic or basic. So if I look at each of these, if you find the cation and anion for all of these pairs in that chart, you'll see that K would end up being neutral. ClO4 would also end up being neutral because perchlorate is the conjugate base of a strong acid. So this is going to have no net effect. Sodium would also be neutral, as would iodide. But you would see that HPO4 minus, you would find that in the list as one that would result in a basic solution. And NH4 plus, you'll find that in the column listing something that would produce an acidic solution. So you'd find those, if I go back here, just clearing this off a little bit. If you were having trouble finding those in your chart, you would see them. NH4 plus would be right there, so acidic, and then HPO4 you'd see right there. So that's how we knew those two. So if I write my reactions for what's going on there, if I interact both of those with water, HPO4 negative 2 interacting with water, it says that this would produce a basic solution, so that must mean that this HPO4 negative 2 is going to gain an H plus, so that's going to become H2PO4 minus, and then left over from the water would be 1 hydroxide ion, and we see that this is why we'd have a basic solution being produced, whereas NH4 plus said that was acidic, so that means this NH4 plus must be donating an H plus, so that would leave us with NH3, which although it is a base, because we're producing H3O plus as well, this is how we know that that would result in an acidic solution overall. So again, you're not responsible for section 16.4 on the test. You can of course read more about this in your textbook. What you are responsible for is section 16.5. So section 16.5 is asking you to think more about predicting the direction of acid-base reactions based on what we know. So we talked about this a little bit in our last chapter, but we're looking at this specifically now in terms of Kas and Kbs. So we know that our acid-base reactions can generally be written like this. If they're weak in some capacity, we'll have this equilibrium occurring, and we end up with a conjugate acid and base on both sides. Now, remember that we talked about this earlier. The bigger the Ka, the stronger the acid. Also, the larger the Kb, the stronger the base. And this is what we talked about last chapter, that if K is less than 1, you are reactant favored. If K was greater than 1, it's product favored. But what we're going to most need right now is this. Equilibrium lies to the side of the equation having the weaker acid and base. So what we'll notice is that if you compare, essentially what we need to do is compare the Kas and the Kbs on both sides of the reaction. And that's going to help us figure out which direction the reaction will go. So equilibrium is always going to go towards the weaker side. Okay? So let's look at one example. If we look at section 16.11, it says write a balanced net ionic equation for the reaction that occurs between acetic acid and sodium bicarbonate. So let's start with that part first. So acetic acid would be HC2H3O2. And we're reacting that with sodium bicarbonate. And we would get two products. We would get sodium acetate, and we would get aqueous carbonic acid. Now, it's asking for the net ionic equation, so the most important thing to note here is that this sodium ion is going to be irrelevant. So when that cancels out, our net ionic equation would be this: acetic acid and just the bicarbonate ion, yielding the acetate ion, and still our H2CO3. So what I see is that I know that this is an acid, and this is going to be a base. So by default, this must be our conjugate base, and this must be our conjugate acid. So those are our pairs. right? That's one pair, that's the other. But if I want to know which direction the equilibrium is going to shift, I need to compare the Ka's and KB's for all of these. So if you look at the table in your textbook that has all of your Ka and Kb values, you also have one in the reference booklet. But if you're looking at the exhaustive list in your textbook, this is table 16.2, and that's on page 595. Make that a little darker, 595. I can list all of my Ka and Kb values. So I'll take a moment and write them all in. All right, and here are all the values you'd find in that table. So we said that equilibrium lies to the side that has the weaker acid and the weaker base. So if I compare all my values here, -5, this acid versus -7. Oops. Sorry, this should say Ka. There we go. So if I compare this acid to this acid, this one's the weaker one. So that's weaker. And if I compare my bases, 10 to the -8th, 10 to the -10th, the smaller the Ka, the weaker the base. So this would, Kb, the smaller the Kb, the weaker the base. So that's our weaker one there. So all in all, because they're both on that side, we could say that the equilibrium lies to the right. So in other words, it's going to shift towards the products. So if you're determining equilibrium shift directions for acids and bases, it's just a matter of comparing the Ka's and Kb's and looking for the weaker side. So that now concludes section 16.5 as well as 16.4.